So first, thank you very much for inviting me. I'm very honored to be here and have this extraordinary luck. So thank you very much. Thank you, Amaury, for everything. So I will indeed talk about quantum automorphism groups of finite graphs. But first, I want to give a bit of a general view of where it fits in the picture. And actually, I want to talk about, so my point will be not so much to focus on the quantum groups themselves, because I will probably not have time to reach until a precise description, but I will talk more about quantum properties. And my aim is that by the end of the talk, one can have in mind what are those quantum properties which appear when studying even finite objects, such as finite graphs, and what can be their interest. And I will mention a link with the cone embedding problem. So I think that's always exciting attention. And I want to keep this in mind. And also I want to keep in mind that combinatorial objects have popped up through operator algebras for now a certain time, but this might be one of the first time that it's not a one-directional process. I want to emphasize that those quantum automorphism groups of graphs have gained interest very recently through recent results, which suggest that there is not only, so usually it was combinatorial techniques giving results in operator algebras, but there have been now results of operator algebras giving things in the world of combinatorics. So it seems to be a two-sense process between those two worlds. So the first one is the world of combinatorics. The second one, of course, that's why we're here, is the world of operator algebras. And what I want to talk about could be called the quantum graph theory. And it sits here. So first I will remind some elementary definitions of graph theory, just so everyone is in the same, with the same settings, because not everybody uses the same definition. So I will make clear which context I'm using. Then I will show how, through the representation of graphs, through the famous adjacency matrix, we can get something more of a matrix flavor. Then, as operator algebras, we turn everything to operator algebras, and we will obtain suddenly this appearance of sometimes quantum properties. Sometimes not, sometimes yes. That would be the point of my talk. So here, what I mean by a graph will always be a finite graph first. It will be, so it is a pair, VE, of two sets. So V here is a finite set. And E is a subset of P2V. Here I just mean the power set of V, but for made of subset of cardinality 2. So I call the elements of E the edges of the graph, the elements of V the vertices of the graph. If I just draw some examples, so we have very famous graphs, which are the complete graphs, denoted by Kn. So you have one for every positive integer, and basically you take n vertices and you put all possible edges. So you obtain those graphs. So this is K4, and so on and so on. Another family of graphs that we'll just sketch here so we have it in mind is the cycles. So it starts for n equals 3, and we represent them like this. So what's practical with graphs is that they have this most computations are done graphically, where we represent vertices by points and edges by straight lines. So in particular, in this context, we're dealing with, they are non-oriented. They are simple in the sense there is no loop, no multiple edges. Yeah, this is really like that. Another example of a graph which will be important later, the official name is K13. And this is an example of a tree. So yeah. Now if we have a graph, we can represent it through the adjacency matrix, so through a matrix. So I just remind the definition, just in case, so everybody is really well in the picture. So here it's a n by n matrix indexed by the vertices of the graph, and we just put a 0 or a 1. according to whether there is an edge or not. So yeah, we can write AXY. It's just okay. We often write an edge as XY. And this is this matrix which will start everything actually. So so now we have a graph. We have graphs, we can represent them as matrices, and actually, when we mean a graph, we don't exactly mean those matrices. We mean the isomorphism classes of those objects. That's very common to do this, this little thing. So here, I just need to introduce a morphism of graph. It's a function which is given by a function on the vertices, and such that it preserves edges. So xy is in E of g, implies f of x, f of y is in E of h. Now those are graph morphisms. If they are bijective, we call them automorphisms. And actually, when we deal with graphs, we never really deal with a set and those things. We deal with the isomorphism class. So actually, for matrices, that will mean that they correspond to when we label the vertices by some integers. And that will play a role in the following, actually. So maybe I just precise that's automorphism, or sorry, isomorphism. So here there is no worry to have about the, it's easy to check that a bijective graph morphism, it's opposite, how do you call it? The inverse function will also be a graph morphism. So this is morphism. Now, how do those concepts translate in terms of the matrices? So actually, there is a very nice description. The point is that
it has to be bijective on edges.
C'est pas clair ça.
Yeah.
F bijective also on E of H.
No.
That's implied.
Bijective on the vertices and not on the edges.
If and only if?
No, that's implied. Because if you have...
Well, I could add edges and then consider the identity map. And it will not
you
be
can map K13 to K4.
So what am I saying?
You have to say bijective on the edges also.
Yeah, you're right. Am I forgetting it? Sorry. Sorry, my bad. I'm a bit confused. So I have something else in mind, sorry.
No, but what I mean is that you take the graph, for instance, you take 4 points, no edge.
Yeah,
and you add all the edges.
No, you're sure. Even you could just, yeah. No, you're totally right. I don't know why I got. I decided that math would be simpler today, but that was a bad idea. No, sure. Bijective on edges too. That's not at all. That's not at all automatic. Yeah, just consider the following inclusion. Okay. Still, in particular, it would be a bijection between finite sets. So that this is for sure. So in particular, if we label them, so let's do that. Let's fix a certain integer n. We take G, a finite graph, H, another finite graph. So well, yeah, V1, E1, E2, E2, and on n vertices. And we assume they're isomorphic. So there is an isomorphism, but actually I will just write it like this. That's abuse, but yeah. If we label everything, we get actually a certain permutation sigma from V of G identified with 1n to V of H through this identification that we've done, 1n. And this sigma can be represented through a matrix, so the famous permutation matrix. So we get P sigma. So this, yeah. And one can write down what it means in terms of matrices, and that means that P sigma conjugates. So here I have, maybe this is the other one which should be the agent. I should not make a mistake. So here I'm probably making a mistake whether the star should be here or not here. The point is the permutation matrices, the permutation matrix here coming from this isomorphism will conjugate the adjacency matrix of H into the adjacency matrix of G. It should be on the other side. Okay, thank you very much. Ah, yeah, of course, since we're starting from H, then we go to G. Yeah, exactly. So, and actually it's even stronger, is that any isomorphism will be given like that. So we can really get them back. And if we take G equals H, I mean, if we take G equals H, we get back the automorphism group that we can describe as the set. We get a commutation relation. So the isomorphisms come from conjugating the adjacency matrix through a permutation matrix, and the automorphisms come from commuting with the adjacency matrix. So this is pretty standard, this is pretty well known, pretty elementary, but that's the combinatorial world. That's where we are right now. Now I would just like to pause for a second and start thinking in non-commutative terms, as one may want to do, and we might replace many of those things here with operators and their counterpart in the operator algebraic world. And then we will get, actually things will turn out pretty well, and we'll get the natural notions of quantum permutations, quantum automorphism groups of graphs, and etc. What I'm going to talk about. And yeah, so let's proceed. So in 98, Wang, so this has been already, thanks to Arthur, mentioned yesterday, so I don't need to go into much details, but Wang introduces the quantum groups, the quantum compact groups Sn+. So this is the permutation group on n vertices. And the point is that he gives the correct analogy with permutation matrices, but in the non-commutative world. And they are the so-called unitary matrices. So let me write classical here, quantum here, permutation matrix, how is it called? Magic unitary. The point is...
What is this magic unitary?
I'm about to define it right now. The point is that, so the coefficients in P sigma are zeros and ones, but 0 and 1s are not operators, so we have to change that. We are operator algebraists. So they are suddenly operators in B of H. So we view them now always as given on a certain B of H. A unitary matrix, U, say on n dimensional, is a matrix such that the UIGs are projections, orthogonal projections in B of H. And they are in such a way that they give partitions of unity on the rows and the columns. So for all I, the sum of the Uij equals 1. For all j, the sum of Uij equals 1. So this is a non-commutative counterpart which actually works for the permutation matrices. We do the same with the adjacency matrix. We see zeros and ones as the unit.
I assume it's unitary, no?
Yeah.
It's automatic.
I mean, the algebra generated by the Uij will be unitary.
No, I am
Matrix.
So the Uijs are also not projections.
Yeah.
But is the whole matrix U, is it unitary?
Yes, that's a little computation. I can say it. Facts.
Ah, because they are projections.
Yeah,
Okay,
they are orthogonal.
okay. No, I understand. No, because I couldn't see where a product of two was involved. But if they are projections, yes.
So they're actually unitaries, and they're magic in the sense that rows and columns sum to 1. So yeah.
And is that equivalent? No. No, of course. I mean, there are many unitaries which are not coming from projection.
Yeah, but actually you can extend some classical theorems. It's equivalent if you ask that the coefficients are positive operators.
So that's what you call magic unitary?
Magic unitary is this, yeah. Yeah, that's what I call. It's been called magic unitary. And yeah, you have many characterizations. Actually, that's a well-known fact that with coefficients numbers, the permutation matrices are exactly the unitaries such that the coefficients are positive. And actually, I could extend, I think, this to the quantum case as well. You can characterize them like that.
They're mutually orthogonal projections, right? They're mutually.
That's implied. This implies the mutual orthogonality.
Yeah, they are mutually for each line and each column, but not globally.
Yeah. If globally they commute, then you could diagonalize everything and you would get permutation things. Yeah. So it's really
Yeah. Okay, it's not a family of ordinals. Yeah, okay.
So now, in the same idea as above, we might ask what happens if we have the adjacency matrix seen with coefficients 0 and 1 as operators. What if we can conjugate two of those adjacency matrices through a magic unitary? What happens? So GH, what about this notion that comes directly from the classical case, quantum isomorphism, let's call it. Which would be, there exists U, magic unitary, such that U adjacency, so here U will be indexed by the pairs of vertices. So let me precise this. XA, so X in V of G, A in V of H. And now I will again make a mistake on which one should be the star, which one should not be the star. Apologize for that mistake again. So this can be easily checked. So I'm not even putting the star now. So it goes from H to G. So I think this time it's here. So we get a notion, an equivalence relation on graphs that is the following. And is it equal to isomorphism? Is it much bigger? The striking thing is that isomorphism is pretty easy. You get the adjacency matrix, you can check it. Actually, in logical terms, it's totally decidable. Quantum isomorphism needs to preserve a lot of things. It preserves the number of vertices. It should send, in some sense, vertices to vertices of the same degree. It should preserve the number of walks. It should preserve a lot of invariance. But it's not equal to isomorphism. And not only is it not equal, the set of graphs, of pairs of graphs, which are quantum isomorphic, is an undecidable set. So that means that there is something really striking going on behind here, and it's very hard to come up with two graphs which are not isomorphic, but quantum isomorphic.
But we want to see one.
Ah, you want to see one?
Yeah.
Okay. They are only the smallest known as 24 vertices, but let's go.
Otherwise,
So 24 is factorial 4, right? So you take S4 as a group, and you take two different sets of presentation, and it's the Cayley graphs which will give the specific thing. So let's call the first one, so the generators. How do I call a set of generators? F. So F1 will be the sigma in S4 such that sigma squared equals 1. F2 will be the sigma in S4 such that sigma is a 4 cycle or a double or
being a 4 cycle is doing a cyclic permutation.
Yeah. Or sigma equals to1 to 2 for some to1 to 2. No, not how do you call that? Transpositions. Yeah. Disjoint transposition. Yeah. Sorry, disjoint transposition. And then claim. I mean, I cannot give you the proof, and I've not even seen it entirely.
No, but you remind us what is gamma. It is a Cayley graph of what?
So gamma here is really my group S4. And I'm about to write G will be the Cayley graph. Okay. I mean, yeah, of gamma F1. And H will be the Cayley graph of gamma f2. And actually, that's a very good idea to put them there because they will appear once more later.
You know, this could play a role in soccer. Huh?
Why?
Because of the 4 teams in each.
Ah.
I am joking.
Well, actually, no. Actually, that's if I may, that's a very interesting point because maybe here you see something which can give an explicit von Neumann algebra of type 2-1 which is not embeddable in ultra power of R. So it's not yet, but ça chauffe devant les buts. So yeah, there is a link with football. I'm about to talk about it right after, actually. Okay. So just to finish about this story, when we get G equals H, here the classical isomorphism, what we get, so we consider the U such that U at G equals at G U. Actually, you can take, this defines a set of relations, and there is a universal sister algebra behind it, and it admits a compact quantum group structure. Yes?
But I just want to ask one question, which is that in the space H that you are taking there,
yeah.
So what is the dimension? I suppose it's finite or is it infinite?
I don't fix it.
No, I understand, but the one that makes this isomorphism here?
We don't know. So we know with infinite, what I'm saying...
No, it's infinite.
No. We know there exists an infinite. I think we do not know if we can take it to be finite. Like we can exhibit one magic unitary which will conjugate the two adjacency matrices. I can also prove that those two graphs are not equal. Like I think one is 4 colorable, the other one is 5 colorable. But I cannot tell you, I mean, I think it's not known whether you can take the coefficients to be finite dimensional or not.
So I have a more precise question. We can take the group now of, which is like the diagonal group, but which is generated by the unitaries associated to each projection. Okay. So, I mean, it's a group which has a representation.
So, sorry, you mean the 2p minus 1?
2p minus 1 for all these, okay? So I get some group. Yeah. And, I mean, when you have this conjugacy, this means you have a representation of this group.
Yeah.
Yes. And so what you are saying is that there will be cases where there will be an equivalence, but it will be with an infinite dimensional representation of this group.
I'm not sure whether we know anything about the dimension. So everything can work in the infinite dimension, what I will say.
Okay. This you know.
But that's actually a thing. We don't know. I think... No, I don't want to say something wrong. But I wanted to say that I think there might be examples of graphs for which are quantum isomorphic, not isomorphic, and we know there is no finite dimensional quantum isomorphism between. But I'm not sure. Okay, I shouldn't have said it because I'm recorded, so. But I do not know. I can give references later, maybe. So now that's very good. I reached here, and I want to say that those come from the representations of a universal sister algebra, which we can equip that actually Danica, if I'm not wrong, equipped in 2004 with a compact quantum group structure that we will call the quantum automorphism group of G. So when G is finite, it's a compact quantum group. And that's what we call the...
Can you say in one word what is the coproduct?
It's the matrix pseudo group. Yeah, it's given by matrices, so actually you have the standard that we saw yesterday, which is... Yeah, it's a compact matrix Uij sent to the sum of k of Uik tensor Ukj. But I will not talk about the... Actually, the point is that already many quantum properties and things like quantum isomorphism can be detected from the algebra without involving too much the quantum group structure. It's necessary at some points, like for R states or things like that, but it's not really what I will talk about. It's not really what I've done. So, yeah. So now that I reached that moment, I will move on to a little interlude. How do we say in English? Interlude. Because I think it's a good moment to give a little motivation. I'm talking for a while about cone embedding problem. So let me mention here one fact. Assume you have two finite graphs, G and H. It looks like I'm in the cave here. There is an object that is called a game which is a finite probability space, I mean, finitely many points. And I won't give the definition, it's not very important here. But this object can witness some properties that I have talked before. So it's very well known that this object can witness isomorphism. This object can witness quantum isomorphism. And actually, that's how we build these. We built an object for which the quantum isomorphism is satisfied, but the isomorphism is not satisfied. And then some other people noticed that, actually, this game that you have built can be represented as this iso GH for those graphs. But we can witness a lot of other properties that are known as correlations or things like that, but that are very well known to be related to the cone embedding problem. And I will not be precise here, but let me call it weak quantum isomorphism. And all those things, what's interesting is that in the case of graphs, we don't need so much to study this game, this object, which is the type of objects that are in this preprint MIP star called ARI. But there are many algebraic things or operator algebraic things that we can see through the structure of the graph already. So we can even forget, many of those things can be studied through those tools that I'm advertising. But what is known is that, in particular, we can witness those things without referring to those objects. But assume I had found G and H2 graphs, so here is the big assumption, which witness a possible difference, so I will put it in another color, here. Then, I was thinking about the color. So assume if iso GH, let's say, separates quantum isomorphism and what I call here, just for this talk, weak quantum isomorphism, then I claim that the B-dual of the quantum automorphism group of G plus H, so here, of course, I take a representation, I take it to be the GNS, is not embeddable.
GNS with respect to which trace?
The R state. In an ultra power of R. So of course, I mean, I cannot give you two. I can give you two graphs which are not isomorphic, but not quantum, but quantum isomorphic. But I cannot give you two graphs which are not separating here. Otherwise, I would maybe giving another talk. But the advantage here is that so even in the strategy which is studied in this preprint MIP star equalary, the point is to come with games which would witness those things. But they don't give any weight for the fundamental algebras to act on those games. I mean, sorry, we just know there will be a fundamental algebra which is not embeddable, which will act on this game. But we don't know which one to pick. But here, through the theory, the algebraic property, the structure, I can give you which one to pick. And this one will be, I mean, a candidate.
What is G plus H?
So, yeah, sorry. I'm using G plus H for an operation known as the, I mean, disjoint union, or sum. So, it's just to, so GH, I have two graphs, G plus H, you take the disjoint union of the vertices, and for the edges, you also take the disjoint union. So basically, if you want K1 plus K2, this is K1, this is K2. This is the following graph. But it's never a connected graph.
Because you want the isomorphism to appear as an automorphism of this graph, right?
Yeah, actually it does, it does. That's a point which has been studied in some papers, that those so-called, I mean, those actions of the fundamental algebras, or actually of what is called strategies behind it, but I don't want to talk too much about it, they appear in this quantum group, and actually they, yeah. So I think that's a big motivation to see that we have to understand when things are classical, quantum, and to which degree. I mean, I think this could be a pretty good motivation. And that's exactly the point of this new field, which got a new, say, impetus in the last years, the main results around those are, I mean, about precise computation, there were very new things in 2019, 2018, and more recent. And one point is that through this, we can maybe understand these separations between, okay, maybe not as much as it, maybe it's too much asking, but already we'll be very happy to understand a bit when things are, can be non-isomorphic, but quantum isomorphic and this type of things. So yeah, this is a bit of a dream on a much simpler, much smaller scale already. A good question is to see when we are classical, when we are quantum. And that's what I want to talk about for the end of the talk. Yeah, the 10 minutes, which I still have, I think. And do I have a place to...
There is a third one.
So, to finish, I want to talk about quantum symmetry, which is really the most basic thing you can ask of distinction between the classical case and the quantum case. And this distinction is very easy. I don't even take two graphs, isomorphism, quantum isomorphism. I take just one graph. I look at its quantum automorphism group, and I ask the question, is this the automorphism group? And through non-commutative theory, I mean, the essence of non-commutative theory, it will appear that it's the same thing if and only if the algebra is abelian. So if and if this universal algebra of the unitary matrices which commute with the adjacency matrix is abelian. So let me write it down. G, a graph. The question is, do we have this? So here, of course, I'm abusing a little bit notations because this can refer sometimes to a sister algebra, sometimes to a dual of a sister algebra in some sense. And this is yes, if and only if Q of G, so yeah, here I'm doing something horrible, I shouldn't, but let's say the algebra is abelian. If the algebra is not abelian, we say G has quantum symmetry. So yeah, that's really a first thing to study. I mean, maybe it doesn't appear. So from all the fancy things I've mentioned, one can guess that some graphs have quantum symmetry. Otherwise, my whole talk would be pointless. But when does it happen? It's very weird. It's very weird because if we start, for instance, so let me choose another color again.
I'm a little bit confused by one thing here, which is that to say that this algebra is abelian, I forgot the definition of the algebra. Does it use the matrix coefficients or does it work already in matrices?
So it works already in matrices. So here, it's the algebra generated by the Uij, which are, so yeah.
Generated by these matrices, not by the matrix coefficients.
So you take the universal one, the universal sister algebra, and the algebra here is the sister algebra generated, I mean, is the universal one. But the point is that
the algebra there is generated by the Uij or?
Yeah, the Uij, sorry. Yeah.
No, okay, this is what I was asking.
Oh, sorry, I misunderstood.
So there is one direction at least which is very clear, which is that if this is commutative, of course, you have projections, so you can go back to the ordinary case.
Yeah, but the converse is also true. Yeah. And actually, the point is that I don't need to exhibit the universal magic unitary. If I find a magic unitary which commutes with the adjacency matrix, then by universality, it will come from, it will be the image of this universal thing. So if I find a magic unitary such that the coefficients do not commute, I know that the universal one is not commutative. No. And the contrary, if I want to prove it's abelian, I just need to prove that all magic unitaries commuting with the adjacency matrix are abelian. So actually, I can a bit forget about the universal object which is hiding behind and just treat magic unitaries, and even with finite dimensional coefficients. So I want to say here, so here, there is...
Why even with finite dimensional coefficients?
No, sorry. I mean, I can do computations if I exhibit a magic unitary.
Yeah, sure,
yeah.
Of course.
I don't need to look for the measure. Yeah. Yeah, totally. And actually, many times it will. So here, there is no quantum symmetry. Here, there is no quantum symmetry. Here, there is no quantum symmetry. Here, there is quantum symmetry, and forever after. And moreover, if this can mean anything, the quantum automorphism group is infinite. Actually, it just means I could write it like that. The dimension is infinite. So it's very weird. Starting at n equals 4, we have things changing. Cn. Cn has quantum symmetry if and only if n equals 4. That's the only one with quantum symmetry. Here, no quantum symmetry. So I'm reaching the end of my talk, and I think I have not attacked the main results. So
no, please state the main.
Just take.
Yeah. So no, I will say, but So here are some results. No, first I need to say something. The thing that we have to check quantum symmetry is that we have a sufficient criterion, and that will be fast. I'll be quick, but we have a sufficient criterion, which is the following: if G has two as Fg classical, such that they are non-trivial, and they are of disjoint support, then it has quantum symmetry. And the point is that in practice, this is always...
Where they are different from one.
Yeah, exactly, yeah. And that's what we observe in practice. Here, you can check it by hand. And actually, in practice, it's almost... Actually, it is not equivalent to quantum symmetry, but that's hard to come up with an example. And that has been only recently done. And so what I thought might be interesting to define is, what if I say that a class of graphs, a family of graphs, satisfies... So this is known as Schmidt's criterion. What if I say that a class of graphs satisfies the Schmidt alternative if in this class it holds that quantum symmetry is equivalent to this criterion? And then here we have, so yeah, we have these results. Cographs, which is a certain family of graphs, forests, sums of trees for those. Yeah, because I'm about to say I should have started with this. Sorry. So there is, of course, my supervisor, so Amaury Frélon. More for the group, the quantum group part. There is Pegapour Najafi, who did the graph theoretical part, and there is me. So that was actually very nice because it was really a collaboration between non-commutative geometry and graph theory. So and there is me, Meunier. So for cographs and forests, they have the Schmidt alternative, and they have even more. They have that the quantum isomorphism is equivalent to isomorphism. And finally, in a work which is supposed to be on the archive very, very soon, we also computed the quantum automorphism groups of those objects. So G cograph, G forest. So those are first example of those objects. And this is our main theorem, I would say.
So you mean there are only cases where this is abelian, if I understand the link with this? So you say the quantum automorphisms are the same as the ordinary isomorphism?
I say this happens if and only if...
But not automorphism.
No. So the point is that if you have a graph in this family, to check if two of them are quantum isomorphic, it's if and only they are isomorphic. Okay. To check if they have quantum symmetry, it's if and only if they have two non-trivial automorphism with disjoint support.
There are cases where they have this, of course. Yes, okay.
Yeah.
So the quantum automorphisms are not combinatorial.
No, because look at the following. I just take K1, 4, next one. This is still a tree, but you can flip here. That's a tree which has quantum symmetry. Okay. So, yeah, that's our main result. And yeah, so cographs are...
What is a cograph?
Yeah, they are very... It's a family that you can define inductively, so cographs. They have many different characterizations. They are actually the first candidates, and seemingly graph theorists would tell you they are the first candidate because they have a very nice structure. So you have K1, the point. If you have G and H, you have G plus H. And if you have G, you have G complement, where by G complement I mean you keep the same vertices and you put edges when you don't have one and you remove them. And with this you obtain a certain family of graphs, and they're pretty easy to describe inductively. I mean, either them or their complement is the sum of smaller cographs. So that's easy to check. For rest, it's a bit more intricate, and yeah, we needed results from other people. And so that's 40 minutes. That's what I wanted to present. I will end here.
Well, are there any questions?
Yeah.
So is it unknown if there are graphs with quantum symmetry but not group symmetry?
I think that's unknown. That's a question I'm wondering myself. When they are in a family which satisfies the Schmidt alternative, that doesn't happen because they don't have classical automorphism, so they don't satisfy the Schmidt equivalent, so they will not have quantum symmetry. So that means it's no for cographs, it's no for rests. But in general, I don't know. I believe it should be the case. Here is an easy example. If you find two graphs which are quantum isomorphic but not isomorphic, take their sum. Sure. You have a quantum isomorphism. The quantum isomorphism will give you a flip between the two. Actually, it's very easy. You put the matrix 0, U star 0. Yeah. That gives you quantum, yeah. But if you can come up with two such graphs, please write to me.
They have to be graphs which don't have ordinary automorphisms.
Yeah. Those have plenty of automorphisms.
Other questions?
Well, I mean, I just want to say that graphs are very simple things in a way. I mean, can one go to higher dimensional objects?
So, I mean, I'm a bit sad because the point of my talk is that even in such simple objects, you already have very complicated...
I mean, they are one-dimensional objects in the sense that as simplicial complexes, they are one-dimensional. So is there a way to extend, my question is there a way to extend this type of issue to higher dimensional stuff?
There is something I looked for, because something which is very... So when computing on forests or trees, what I wanted naturally to do is to add some constraints saying, okay, I want quantum automorphism which fits, yeah. And I had a lot of trouble finding a correct notion. So eventually but recently I noticed is probably what is known as hypergraphs. So hypergraph, but one has to know that actually you can...
So I was really thinking about higher simplicial complex.
They are hypergraphs.
Oh, they are?
They are hypergraphs, but every hypergraph can be modelized with a graph. So a hypergraph, I mean, it's really... I will call it, I don't know, omega. So V here is a set, and omega is a subset of P of V. So topological spaces are hypergraphs.
Okay, good.
Yeah.
But normally for a simplicial complex, it's hereditary. It's an hereditary family of subsets.
Yeah. Well, you can...
It's not true for hypergraphs. Yes.
Well, you can consider the hypergraphs which have those things. But are you asking that you start with an infinite set of vertices also?
No, not at all.
Yeah. If you stay finite.
Finite sets.
Yeah.
There are, billions of very interesting examples of simplicial complexes.
Yeah.
I'm just asking whether this type of, under quote, quantum treatment could be extended.
But I don't think you will find anything new, because as long as you start with something finite, you can represent it through a graph, actually. Those are standard constructions. Like, if you assume you have your objects, which has...
No, you can, but I mean, you are losing some structure. I mean, it's not true that if you think of higher simplicial complex as a graph, you are losing some stuff. You are not preserving the right property. Because
you should not think with the spontaneous graph. My point is you can define a transformation which will bring you should not take the same set of vertices.
No, I understand. I understand. But, okay.
Sorry, maybe I'm not understanding the...
No, what I have in mind is that, okay, graphs are fine because they are defined relations and so on, but there are many instances in which one has something a little bit more specific than just a graph, and in which one would have a lot of interest to find some quantum symmetries.
Okay.
That's what I have in mind. So it's a more general thing. You see.
Okay. Could you give me an example?
Well, for instance, what I have in mind, which motivates me, is that if you look about the standard model in physics, for instance, it is interpretable in terms of something very combinatorial.
Okay.
And normally one only looks at it from the ordinary notion of symmetries.
Okay.
So I mean, if one could, this has not been done at all, but if one could, using this type of idea, except that in this type of idea, I'm not quite convinced yet about the fact that you take projections when you take the ingredients of the magic unitary. I would like to be convinced by this. I mean, okay, in a sense, what you are doing, you are using the logics of the, of the quantum, because your projections are just the logics of the quantum, which is not the ordinary logics. But still, I mean, I'm a little bit.
You would like to take positive operators?
No, but you say that if you take positive operators, so it's a kind of mixed between positive and unitary, which is.
Okay. Well, I don't know about that. I'm not the one responsible for the definition. I've just worked with it. But of course, I'm very interested if there are more natural options.
Okay. I mean, what I'm saying is that it shows, at least in this case, that it's very fruitful to go beyond the ordinary isomorphism.
Yeah.
That's what it shows.
Yeah. The fact that it becomes undecidable, I think, is very. And actually, so I've not at all talked about quantum isomorphism itself, but there is a very recent result which uses operator algebras to prove something, graph theoretical question, which is the other side of my, which deals with that.
But if you fix the dimension, if finite, is it still undecidable, or I doubt that?
No, it is decidable. That's the point. But the point is that. Yeah, and even worse, the guess is that normally this is where you see it. If you take the function which up to goes send number of vertices to the dimension witnessing the thing, this should be a function which is not decidable, meaning it is not in the clean class, in the class of recursive functions. So maybe here I'm saying something totally wrong, but from diving into the preprint Lipstack corollary, that might be, from talks I've had with people, one place where we would witness is that when you take the dimension.
What you are saying is that this dimension cannot be written down. It's not a recursive function. That's what you're saying.
It can be written down with usual recursive logic. I mean, it can be written down. It cannot be written down from the function n gives n plus 1, projecting on the coordinates, constant functions, and allowing induction, composition, and a kind of minimization operator.
But is the gross known or something like that?
Absolutely nothing is known. This is a guess if the strategy outlined in the paper Lipstack corollary can be understood and applied here. That would be the guess. Because actually, if the answer to the cone embedding problem were true, it's normally this function should be decidable. I think so. But here I'm really, I don't want to say, I'm saying it on camera, so that's my bad. But I don't want to say, because it's really like things, conversations. Okay, so between us, I have the feeling from the discussion I have had that this is exactly this dimension function. That if all to one were embeddable. Yeah.
Okay, thank you. So,
Thank you.